Then angular distribution and polarization measurement. In this section, we consider the experimental techniques that helps us to distinguish one multipole from another. To determine the multipole order of gamma radiation, we must measure the angular distribution of the radiation. And to distinguish electric from the magnetic radiation, it is necessary to do additional measurements, such as to measure the polarization of the radiation. By way of illustration, let us consider a dipole transition from II equal to 1 to IF equal to 0. The initial state includes three sublevels with Mi equal to plus 1, 0, minus 1. The final state has only one sublevel with Mf equal to 0. അപ്പോൾ നമ്മൾ ground state നമ്മൾ IF എടുക്കാം. അപ്പോൾ magnetic quantum number Mf is equal to 0. Then II has three, it is a triplet, three states, plus 1, 0, minus 1, or minus 1, 0, plus 1. Okay, excited state, three states, triplet state. For example, in the case Mi equal to 0 to Mf equal to 0, the gamma emission probability varies as sin square theta. The transition from Mi equal to plus or minus 1 to ground state Mf equal to 0 have angular distributions that vary as half into 1 plus cos square theta. If we could pick out one of the three initial M states and measure the angular distribution of only that component of the transition, we would observe the characteristic angular distribution. The simplest scheme to do this would be to place the nuclei in a very strong magnetic field, so that the interaction of the magnetic moment mu of level II would give a splitting of that level depending on the relative orientation of II and the field beta, and the field B. And this is analogous to the Zeeman effect in atom. Okay. Okay. Splitting of the level into 3 plus 1, 0, minus 1. MFI is ground state. Okay. But we cannot resolve the transition from the other two states. Before the field is turned on, there is one transition energy. When the field is present, the splitting of the levels gives three transition of energy E, E plus delta E, and E minus delta E, where delta is mu V. If we could pick out only the component with energy E plus delta E, for example, we would see the half into 1 plus cos square theta distribution relative to the direction of the field. We can estimate the magnitude of delta E minus for delta E for a typical magnetic moment of one nuclear magneton in a large field of 10T. Delta E approximated to 10 power minus 6 eV. This small value of delta E is far below the energy differences we can resolve with gamma ray detectors, which typically cannot separate or resolve transitions within 2 keV of each other. Thus, what we actually observe is a mixture of all possible Mi to Mf transitions, that is plus 1 to 0, 0 to 0, minus 1 to 0. If we let W of theta represents the observed angular distribution, then W of theta equal to summation Mi P of Mi W Mi to M of theta. where P of Mi is the population of the initial state, the fraction of the nuclei that occupies each level. That is the population of the initial state. Under normal circumstances, all the populations are equal. P of plus 1 equal to P of 0 equal to P of minus 1, which is equal to 1 by 3. So that W of theta is proportional to 1 by 3 into half into 1 plus cos square theta plus 1 by 3 into sin square theta plus 1 by 3 into half into 1 plus cos square theta, which is a constant, right? That is, the angular distribution disappears and the radiation intensity is independent of direction. And internal conversion. Internal conversion is an electromagnetic process that competes with gamma emission. In this case, the electromagnetic multipole fields of the nucleus do not result in the emission of a photon. Instead, the fields interact with the atomic electrons and cause one of the electrons to be emitted from the atom. സംഭവിക്കുന്നത് വെച്ചാൽ ഗാമ emission gamma ray and the photon and all that interacts with the outermost the electrons around the nucleus. Then that electron goes to the excited state. That means that will be ejected out from the nucleus. The transition energy delta E appears in this case as the kinetic energy dE of the emitted electron plus the binding energy B that must be supplied to knock the electrons loose from its atomic shell. That is TE, kinetic energy of the electron is TE is equal to delta E minus B. Following the conversion process, the atom is left with a vacancy in one of the electronic shells. This vacancy is filled very rapidly by electrons from higher shells, and thus we observe characteristic X-ray emission accompanying the conversion electron. For this reason, when we study the gamma emission from a radioactive source, we usually find X-rays near the low energy end of the spectrum. In some cases, internal conversion is heavily favored over gamma emission. In others, it may be completely negligible compared with gamma emission. As a general rule, it is necessary to correct for internal conversion when calculating the probability for gamma emission. That is, if we know the half-life of a particular nuclear level, then the total decay probability lambda t is equal to 0.693 by T half. T half is half-life. Has two components, one lambda gamma arising from the gamma emission and the other is gamma E arising from the internal conversion. Therefore, total gamma T equal to gamma lambda, and lambda T equal to lambda gamma plus lambda E. The level decays more rapidly through the combined process than it would if we consider gamma emission alone. It is convenient to define the internal conversion coefficient as alpha as lambda E by lambda E by lambda gamma. That is, alpha gives the probability of electrons emission relative to gamma emission and ranges from very small to very large. The total decay probability then becomes lambda t equal to lambda gamma plus gamma into 1 plus alpha. We let alpha represent the total internal conversion coefficient and define partial coefficients representing the initial atomic shells. That is, lambda t equal to lambda gamma plus lambda ek plus lambda el plus lambda em and so on. So we can write lambda gamma into 1 plus alpha k plus alpha l plus alpha and so on. For alpha equal to alpha k plus alpha l plus alpha m and so on. Of course, considering the subshells, we could break these down further, such as alpha L equal to alpha Li plus alpha Ln plus alpha Lm. Similarly, for other shells. Okay, others